question, and that is if we launch a projectile from the base of an incline that rises at some angle phi, what is the launch angle theta that will maximize the distance along which this projectile travels? So we would start this problem at the same place we did before, where we write down the equations of motion for the projectile in the x and y directions. So the y coordinate would be v sine of theta times t minus 1/2 gt squared. The x position will be given by v cosine theta times t. All right, so as before, we need an expression for the time at which this object lands, and I'll just run through that again for those who didn't watch the previous video. We need the object to land somewhere along this line, whose equation is given by y is equal to tangent phi times x. So if we plug in our two expressions for the x and y positions into the equation for this line, we get v sine of theta t minus 1/2 gt squared is equal to v times the cosine of theta times the tangent of phi multiplied by time. And then we eliminate one factor of t from everything, do some rearranging to solve for the time when this thing lands. So the two steps I showed there, where 1/2 g times t is equal to v times the sine of theta minus cosine theta tangent phi, which gives us t is equal to 2v times sine of theta minus cosine theta tangent phi, all divided by g. Okay, so we need to maximize the distance at which this object lands. So we can make things a little bit easier by realizing that that's equivalent to just maximizing either the x or y position. And I'm going to work with the expression for the x position because it's a little bit simpler. So the x position at which this thing lands, I'll call that x final, is going to be v times the cosine of theta multiplied by this expression that I have here. So 2v squared, and then I'll have sine theta cosine theta minus cosine squared theta tangent phi, all divided by g. So I need to find the value of theta which maximizes this expression here. And that's equivalent to just maximizing this expression here in parentheses since everything else is constant. So I'm just going to dispense with the 2v squared divided by g and just focus on this expression in parentheses here. What is the value of theta that maximizes that expression? All right, so one thing I might do here is actually keep the factor of 2 so I can make use of a trig identity. So let's say the x final is proportional to 2 sine theta times cosine theta minus 2 cosine squared theta tangent phi. That first term is just the double angle formula for sine. So I can write this as the sine of 2 theta minus 2 cosine squared theta tangent phi. So now I can take the derivative of this expression with respect to theta. So we have to know how to differentiate sine and cosine. The derivative of the sine of some function is the cosine of that function multiplied by the derivative of whatever is inside. So this will be 2 times cosine 2 theta. And then the derivative of cosine is negative sine. So applying the chain rule here, we will get minus 2 times of 2 times the cosine theta multiplied by the derivative of cosine theta, which is negative sine theta times the tangent of phi. Okay, so we can clean things up a little bit. We have two minus signs that will cancel each other, and then we actually have the double angle formula for sine here again. So when I clean this up, this will be 2 times the cosine of 2 theta plus 2 times the sine of 2 theta times the tangent of phi. And to maximize this expression, I want to set that derivative equal to 0. Okay, so I can move some things around to get everything in terms of theta on one side of the equation, everything in terms of phi on the other side. And if I do that, I will get, let's see, 2 times the sine of 2 theta tangent phi is equal to the negative 2 cosine of 2 theta, which gives me up here the tangent of phi is equal to the negative cotangent of 2 theta. Now, this can be a little bit challenging here to extract a more direct relationship between theta and phi from this expression. I can write this maybe another way using the relationship between sine, cosine, and tangent. So I'll have sine of phi over cosine phi is equal to negative cotangent 2 theta, negative cosine 2 theta over sine of 2 theta. Now, it seems like we might be stuck here, but if you are familiar enough with the unit circle, you may spot something here. We're basically looking for two different angles, phi and 2 theta, such that the sine of one angle is the cosine, or the negative cosine of the other angle, and the cosine of one angle is equal to the sine of the other angle. And it turns out that the solution to this is that we have two angles which differ by 90 degrees. So just to review some lesser known trig identities here, if we have the sine of some angle plus 90 degrees by using the summation formula for sine, this turns out to be equivalent to the that would be sine of theta times cosine of 90, which is 0, plus cosine theta sine of 90, which is 1. So this is just equal to the cosine of theta. And then if I take the cosine of some angle plus 90 degrees, again, by applying the summation rule here, that would be cosine theta times the cosine of 90, which is 0, minus the sine of theta times the sine of 90. So this is equal to negative sine of theta. All right, so what that means is I can write down that the sine of phi, for example, is the same thing as the cosine of phi plus 90 degrees, or the negative cosine of phi plus 90 degrees, and then the cosine of phi would be the same as the sine of phi plus 90 degrees. So rewriting what I had before, I've got negative cosine phi plus 90 over the sine of phi plus 90 is equal to negative cosine of 2 theta over the sine of 2 theta. And this is clearly going to be solved when 2 theta is equal to phi plus 90 degrees. So that is our solution. We can divide through by 2, and up here I'll have my answer. Theta, the launch angle, is equal to 45 degrees plus half the angle of our incline. All right, so that is a very tough problem, but the answer does make sense. When we are firing along level ground, we get the result that we expect, where the optimal launch angle is simply 45 degrees. But as the angle of our surface increases, the optimal launch angle increases as well. But notice you can convince yourself that whatever the angle of this incline is, our optimal launch angle will always be somewhere between 45 and 90 degrees. So we never get a nonsensical answer like 100 degrees firing backwards as the optimal launch angle. So this result makes sense, and that is, in fact, the solution to this problem. All right, so thank you all for watching.